days are the hardest days. Don't you worry anymore. Cause when life looks like easy street, there is danger at your door.
Hey again, everybody. Welcome here to Lesson 8 of Chem 127. This is the turning point in the course where we leave the fundamental chemistry and physics and earth science behind, and we begin to apply the tools in that toolbox to understanding the climate system. And if you're hearing this from the standpoint of a physical chemist, that means understanding the radiation balance. And what we're going to do here for the next few lectures is we'll set up this sort of cosmic system, and you'll see this here, where we sort of, follow the light as it trickles in from the sun to the earth, and then either bounces off or gets re-radiated and has to be passed through the atmosphere before it goes back to space. And we'll phrase this as a series of questions about, hey, what's going on? What kind of light is there? What's doing what? And you'll see those in a second. After we set up that sort of macroscopic version of the discussion, we will start talking about the incoming radiation and what happens or what causes some of it to bounce off, sort of be reflected back to space. There's some excerpts of this EM book to sort of read, and this is in homework number 5. So now, one of the handouts that I asked you to print out is something that looks a little bit like this. This is an older version, but it's got a series of questions on it. And the first thing we're going to do through here is go through the first part of these, because essentially what we're going to do here, shifting to this picture, is we're going to follow the radiation in through the atmosphere and ask questions about what happens, and then we're going to follow it back out and ask questions about what happens. And these questions sort of, raise the key issues that we need to think about to understand climate, but then also kind of show how that fundamental stuff that we learned connects to these issues of the global climate balance. So let's take a look at this graphic here, which is what I like to call the big picture. Okay, so we've got 3 parts to the story here. We've got this, a medium-sized star, 93 million miles here to the left, called the sun. We learned in the last fundamental lesson that it's radiating a bunch of light, the majority of which is visible, and some UV and some IR that's near the some IR that's very near the visible that we might call near IR in the business. And that's the light that's coming out of the sun. A very, very small fraction of that actually intersects the Earth, right? Because the sun is radiating in all directions. So this one little beam is the one that happens to hit the Earth here. 2 things can happen to that light that's incident on the Earth. It can either be reflected, which means it bounces off with no effect. It's like hitting a mirror or a bright surface or something and going back to space, thereby not affecting the climate, not warming the planet at all. The part that's absorbed by the Earth's surface or by the atmosphere then is energy that's a net input into the Earth system, and to maintain a constant temperature, the Earth must subsequently get rid of that, and it actually gets rid of that by re-radiating that radiation as infrared radiation. So there's kind of a cosmic transformation process going on here. We've got UV and visible going in, some of that UV and visible bouncing off, mainly visible because the UV gets absorbed in the ozone layer by and large. And then for that energy that gets swallowed up mainly as visible visible radiation, it must be re-radiated as a different kind of radiation. And this, again, all has to be in balance to maintain a constant temperature. And there's 2 ways to frame that balance. Okay, and if you're taking an accounting class, this will make sense here. I mean, we need to have both sides of the balance sheet equal, right? So we've got this incident radiation, and if the temperature is going to stay constant here, the energy coming in as radiation needs to be balanced as the radiation going out. Okay, so the total incident radiation can be said to be equal to the amount that bounces off, the reflected radiation, plus the re-radiated infrared radiation of the Earth. That needs to be in balance. Another way to express the balance, which is sometimes more convenient, is that if we were to effectively take the reflected here and subtract it off both sides of the equation, okay, and by incident absorbed, I mean let's take the incident radiation and let's subtract the reflected from it. That part is the part that gets absorbed, and that part that's absorbed needs to be re-radiated. Okay, but again, there's different kinds of radiation here. There's UV visible, UV invisible incident. The UV actually gets absorbed in the atmosphere. This part of that visible bounces off the surface in the clouds. Part of it enters the Earth system. The Earth then re-radiates infrared radiation. Okay, and those are key aspects. Okay. Here's a fancier picture of the same thing that I stole from the United Nations website and from the EPA website. And you can see that there's a distinction here between what goes on in the atmosphere and what goes on the surface. And we'll make this distinction important in a second as we go through here. But as this light goes in, there's actually two distinct places it can bounce off. It can bounce off things in the atmosphere, as we'll see that's mainly cloud, or it can bounce off the surface. Incoming radiation can also be absorbed somewhere in the atmosphere, and the brunt of that is UV absorption in the ozone layer, or it can be absorbed by the surface. And the outgoing radiation can also be absorbed in the atmosphere, and that process is called the greenhouse effect. Some of that gets sent back to the Earth, and it needs to be re-radiated again, and so on and so forth. And that is the atmosphere, sort of like acting like a dam in a river. And that, you know, at some point the flow is going to equalize, but the atmosphere is trapping that heat until the heat level builds up a little bit, kind of like the water level building up behind a dam, and then the flows become equal again when the dam has as much water behind it as it's going to hold. So you can think about the air and the atmosphere trapping sunlight the same way that a dam traps water in a river. Okay. Moving forward here, let's see these questions. I'm just going to answer the first couple of them, but let's go through them. So we might ask a question like, what wavelengths are emitted by the sun, such that what is that incident radiation composed of? Which reach the surface? You know, which make it through the atmosphere to the surface, which get absorbed, and why? And for that matter, which ones are reflected? Okay. What's going on that absorbs some of that light in the atmosphere? Where is that stuff in the atmosphere? And if human activities affected that, because if there's things absorbing incident radiation, it's going to affect the radiation balance. And the key thing we're looking at here is how human activities might have affected things in the atmosphere that affect the radiation balance. And then, you know, what chemical processes are going on? Does that absorption process here create any interesting chemistry for us to learn about, or for that matter, have the human activities, are those human activities affecting that stuff that's there by any chemical mechanism? And that's kind of the whole story. We know the answer to the first question because we know that the Earth is a 5800 Kelvin black body, and it's going to emit mainly ultraviolet and visible. Okay, and the peak wavelength is right in the middle of the visible spectrum, but it's mainly that higher energy light that can do photochemistry and not the lower energy light, which reaches the surface. Well, as it turns out, wavelengths longer than 300 nanometers reach the surface, and wavelengths shorter than 300 nanometers get absorbed in the ozone layer. So this is the cutoff that's a little bit below the UV. So the UV that goes between 300 and 400 nanometers actually makes it all the way to the surface. The UV that's below 300 nanometers gets absorbed in the ozone layer and does a bunch of stuff there. Stay tuned. We will talk about chemistry of the ozone layer in the next lesson. This lesson, we're going to focus on the reflected radiation. Okay, but before we go that, let's just go back to this big picture and say that, you know, if there's three parts to the story, there's three parts in which three things that could change in the most general sense that could affect global climate. One is that we could change in the incident solar radiation. The sun become brighter or dimmer, or there could be a change in the geometry between the Earth and the sun. The orbit could fluctuate such that the amount of solar radiation reaching the Earth to begin with would change, and that would affect the temperature, because if there's less energy going in, it's going to get colder, and if there's more energy going in, it's going to get warmer. This is part of the story, especially over the long term. We could, or something could, affect the fraction that's reflected, that bounces off. This also is part of the story. When we make changes to the Earth's surface, or there's a change in cloudiness, or there's a change in the amount of ice cover, this affects the shininess of the Earth, which we'll call the albedo in a second, and that affects climate. If more light is bouncing off, it gets colder. If less light is bouncing off, it gets warmer. Okay, we could affect the degree to which the re-radiation process is effective, and the way we can affect that is by increasing the height of the dam. All right, if we have a thicker, less transparent atmosphere to that infrared the Earth is going to get warmer. In other words, if we trap outgoing infrared radiation like a blanket by enhancing this thing called the greenhouse effect, it's going to get warmer. If the atmosphere is thinner in that respect, if we impede or lower the greenhouse effect, the planet's going to get cooler. And we will look at all of these things, and by all means, scientists have looked at all these things too. There seems to be a misconception out there that the only thing scientists have ever looked at is the greenhouse effect and have tried to explain climate in terms of that alone, and that is by no means the case. The people that are doing this work are not that ignorant. Okay, so let's move forward here. We're going to focus on things that can affect the fraction reflected, which might be the simplest in terms of the physics, but by no means is a trivial part of the story. And for that matter, we're going to break that into two parts. We can talk about things that might be floating around in the atmosphere that might reflect light, and we're going to separately address things that are happening on the surface. There are both natural parts of these processes, and there are both human parts of this process that have been affected by human activity. Okay. To get a little more technical here, I'm going to introduce this term called the albedo. The albedo is simply a term that represents the fraction or percent of incident radiation that gets reflected. A 0.3 or 30% is the global average, which is to say, in total, atmosphere, land surface, and the whole bit of all of that incident radiation that hits the Earth, on average, 30% bounces off and goes back to space, and thereby does not affect the energy balance of the climate, or the energy balance of the Earth at all. The part that warms the planet, or as a net energy put into the planet, is that 70% that doesn't get absorbed. Okay, moving forward here, let's just quickly talk about surface albedo. So in other words, let's talk about the piece of this that goes through the atmosphere and strikes the Earth's surface and then bounces off. And just take a look at the various things out there, types of surfaces that are out there, and the degree to which they reflect. Again, if you look at this chapter and this table, and this is from the Essentials of Meteorology reading, you can see Earth and atmosphere together. That's the average of the surface of the Earth and the atmosphere is about 30%. Okay, that means 30% of the light bounces off. You can see that, Venus has got a very high albedo. Mars has a slightly lower albedo. As we go forward a little bit here, we'll actually compare those three planets directly. The clouds here we'll talk about in a second, but clouds are white, and the low range of the albedo is 30%. The high range is 90%. Clouds have varying thicknesses and varying darkness. I mean, a storm cloud is really dark, and other clouds are puffy and white, and that's variable. But look at some of the things on the surface of the Earth here. A forest is this dark green color. It's very low albedo. A farm field is also relatively low albedo. A grassy field is slightly higher albedo. A sandy desert is higher albedo. Ice, snow, relatively high albedo. I mean, fresh snow is 85 to 90%. So the point is that, depending on what's covering the ground, it's going to affect the degree to which the radiation bounces off. And indeed, human activity has affected these things. As civilization has occurred, among other things, we've cut down forests and replaced them with farm fields. We have mismanaged some farm fields and some grasslands in places like Africa, and deserts have expanded. And this has had a net increase in albedo. So these surface and land use changes, in terms of how they've affected the albedo of the shininess over the past 2 centuries, have made the Earth more shiny, and the net result has been a slight cooling effect. One of the more significant anthropogenic cooling effects on the planet. Now, there's another land use effect that has to do with cutting down forests, and when we cut down trees and they stop eating CO2, that affects the greenhouse effect, and that has by all means led to a warming effect, but I'm not talking about that here. I'm only talking about the effect on how shiny the Earth's surface is.